Today on Electronics Tinker, I'm going to be showing you the schematic and board layout for the 1541 emulator. So last year when I got my Commodore 64, I was really excited to start programming it, and after replacing a bad RAM chip, it appeared the computer was fully working. And that's great, except I didn't have any way to save or load programs to it, and that's sort of a problem if you're trying to write programs for it. So I looked around on the internet and I decided I didn't really want to go with an actual disk drive, but there was also another option to get like an SD to IEC adapter, and I was considering buying one, except I was thinking I might be able to build one myself. Now, this was a little bit ambitious at the time because I'd never programmed anything besides really sending something over the serial port with an Arduino or like blinking an LED. So this was definitely something new for me to try, and I was kind of excited to try it. So over a winter break, I got my Commodore out, and then I also got an Arduino UNO with an SD card shield, and I got to work programming it. Over the course of about 4 days, just solid working on this, I managed to get a basic driver working where I could load and save programs. It still had some bugs and occasionally wasn't recognized and things, but it was working. So I decided to go on and at least get the schematic drawn out. So here's the schematic that I ended up drawing out. There's been a couple of changes in here, such as adding an air LED and adding the crystal in and things like that that weren't actually on the original Arduino setup, but I decided might be really useful in a future setup if I were to ever create a board out of it. So just a brief overview of the schematic. We have an oscillator section here, so it's the 1 megahertz oscillator or crystal with the two 22 picofarad capacitors along with a 1 mega ohm resistor in parallel. There is an ICSP port so that I can reprogram the Arduino chip without having to unplug it from the socket. The main chip I'm using is the ATmega 328, so the same chip that's used on the Arduino UNO. In replacement for the SD card shield, I'm using just a standard SD card socket. It's an SD card micro. And then instead of using a chip to shift the logic levels between the microcontroller and the shield, I'm instead using a resistor divider. And the reason for this is I've never done surface mount soldering before this project. So I wasn't sure if I could actually get a chip to solder to the board correctly, so I decided to play it a little bit safer and instead go with a resistor divider. Additionally, there is an RJ11 jack. This connects to the serial port on the Commodore 64, and this contains the data clock and ATN lines that are needed for the IEC bus. It also contains the external reset line, which will, if you solder over this jumper on the board, it will automatically reset this disk drive when the computer resets. Otherwise, if this is not soldered, then the disk drive will only reset when you hit the reset button. Also, there is a serial port, so it just contains the RX and TX lines off of the Arduino, but it also contains the reset line and ground. And finally is the two card edge connectors. So here's the female card edge connector. We pull the power and ground off that, and then the male card edge connector is on the other side. The power supply for the SD card is 3.3 volts, so that means I have to add a regulator in here somewhere, because the Commodore doesn't have a 3.3 volt supply. So on the board is a 2.2 microfarad capacitor across the two input lines, so the VSS and VCC. And then also we have a power LED. So it's just a green LED with a 470 ohm resistor in series. And this tells you that the computer has power. And then I have an LP29050Z regulator. So it's a low dropout regulator. And I chose this over a normal linear regulator, like a 7800 series regulator. And the reason for that is I'm feeding this regulator with 5 volts. And if I would feed a normal linear regulator using 5 volts, the voltage output would not be what I need because it's below the dropout threshold. So I had to use a low dropout regulator in this situation. This one in particular is rated to 100 milliamps, and that is more than sufficient for this application. And then finally on the output, I have a 0.22 microfarad capacitor, which feeds straight into the microSD card shield. A few notes on the schematic. The ICSP port, because I'm using this resistor divider, can only be used if the SD card shield is, or the SD card is not plugged in. And this is because the ICSP port uses the 5 volt logic levels, but the SD card uses 3.3 volt logic levels. And if the ICSP port were to have a 5 volt signal on the MISO line, because that goes straight into the SD card shield, it could potentially damage the card. So whenever using the ICSP port, it's best to make sure the SD card is removed. Also, as I mentioned before, these two solder pads are separate by default, but if they're soldered together, so you put a blob of solder right over them, that will connect the reset line of the ATmega to the reset line on the Commodore 64, so that it will reset if the computer resets. Switching into the board layout view, you can see here's the whole board, and we have the male cartridge connector and the female cartridge connector on this side. These are the solder pads that the main connector connects onto, or solders onto. Also, we have the power and air LEDs, the ICSP port, reset button, the dropout regulator, along with the reset button debounce capacitor, and the linear regular output regulation capacitor. Here is the resistor ladder to divide the voltages from the 5 volt logic levels to the 3.3 volt logic levels. We also have the two bus pull resistors. So these are pull-ups on the IEC bus, which is connected to this RJ11 connector. The diode here is used just to prevent this reset button from pulling the reset line inside the computer low, but the reset from the computer can pull this reset line low. So it's sort of like a one-way OR gate. Also, here is that solder pad that I was talking about, where you can solder a blob across that, and then that will enable the reset with computer. Also, here is the 16 megahertz timing crystal with the two 22 picofarad capacitors and the 1 mega ohm resistor. We also have the serial header, so the RX line, the TX line, reset, and VCC or VSS, as well as the input capacitor. So this is just a filter across the power lines. We also have the revision number, so this is revision 1.1, and then the batch number is a block here, and then that will let me write in what batch it is. So if I order a set of boards that is, say I order a set of boards in February, and then I order another set of boards in June, I can put batch 0 on the February ones and batch 1 from the June ones, so that I know if maybe there's a problem with the second batch or something, I know all the boards from this batch could potentially have that problem. So that batch number just kind of lets me know which set of boards that were manufactured are related to each other. Also up here we have the 1541 emulator, just the text, and on the back we have the electronics tinkerer. One thing to note is I've added these two holes here, and these are for adding stress relief to the board. So when the board is sitting in the back of the Commodore 64, it's a sort of a cantilever, and especially if you have a cassette drive connected to this end, that can be a lot of force put on that connector on the back of the Commodore. So to prevent breaking that connector or damaging the board in any sort of way, I've added these two holes where standoffs can be screwed in, and then that will hold up the back end of the board while it's plugged into the computer. A few things to note about this board. The dimensions are 40 by 80 millimeters, and originally they were going to be about 40 by 60, but I found with all the through-hole components and everything, there was just no way I was going to be able to fit all of them on the board that small. In a future revision of the board, I would like to make some of the components surface mount, and then that would allow me to shrink the board even further and also put more features onto the board. So, for example, the 18 mega could be shrunk down a lot more if I'd used a surface mount version, as well as using the LEDs, the resistors, and some of these capacitors, as well as the timing crystal. They could all be used to surface mount, and that would reduce the amount of board area by a very large amount. And it would also mean that I could put components on both sides if I really wanted to. That would also let me put some more features on the board that I didn't get to because I felt like it was making the board too large. One of those included putting an ESP2866 module onto the board so that this could host its own web page on your local network, and so I could send files over to it without having to unplug the SD card. At the time, that was something that was just kind of something I was not really even thinking I would ever do. But now that I've got the board designed, I might consider doing this in the future. Also, during the process, this was definitely not without its problems. One major thing was routing all of these signals here, these 4 signals, from one side of the board to the other. Because as you can see, there's quite a bit of stuff on the board. I mean, it's definitely not the most compact board anyone's ever seen, but it does have a lot of components on it. So routing all of them from one side to the other involved a lot of reworking signals, as well as adding in quite a few vias and things of that sort. That's all I have for this video. If you liked it, be sure to leave a like, comment, or maybe even subscribe. In the description are links to the overview, demo, and build videos for the 1541 emulator.